Okay, good afternoon, everyone. As usual, I start by asking you about your homework. Please put, if you have questions about the homework, put them on chat and we can go through them. Okay? All right. While you guys put your questions, I need to address one main mistake that you guys did on your quiz. And here is the mistake. There is a mistake in using this property, log of a to the n. So that's the mistake on your quiz. Okay, log of a to the n is equal to the power n goes down, so it's going to be equal to n times the natural log of a. What it's not, which is I saw, it's not you take the whole expression and raise it to the power n. That's what the mistake that showed up is. You take the n and you bring it down and you multiply by ln of a. So what do I mean by that? So what I mean by this, the following. Suppose I have ln of 2 to the power 3, for example. Okay, this is equal to 3 times the ln of 2. You multiply by 3. It's not ln of 2 to the power 3. They're very, very different thing. You multiply ln by 2. You don't raise it to the power 3. So that's really wrong. So ln of, let us say, 2 to the x goes down, and then you multiply by the ln of 2. Okay? So the mistake in your quiz was the following. I told you, okay, suppose ln of a is p and ln of b is q. Just I gave them a name. And I asked you to express the following in terms of p and q. Okay. So since here I have a product, a multiplication, the log will take that to the sum plus the ln of b to the power 4. Okay. And the mistake comes up here. So this should be ln of a plus this 4. It doesn't become a power. This 4 goes down here and become 4 times the ln of b. Okay. And this will become p plus the 4q. Okay. The mistake that I saw several students did it is that when they took this expression, they put ln of b to the power 4, making it p to the power 4, which is wrong. Making it q to the power 4, which is wrong. It's 4 times q. Okay, for those who did this mistake, please make sure you do not repeat it. All right, so with this being addressed, now I look at your problem and then we proceed. So I'm going to do number 11. Section 4.2. Number 11. Okay, let's see what is it about. The population of a town is decreasing. So population is decreasing at a rate of 7% per year. So it's decreasing at the rate of 7% per year. Means every year it loses 7% of its population. It means it keeps 93% remain. So 7% are gone. So every year it's 93% of what it was the year before. So the question is, how long does it take for the population to be cut in half? So this is my population. Okay, so how long for population to be cut in half? So it's a little bit, it's not hard, but it's a bit confusing. They do not give me the initial population. The problem doesn't give me. But the problem is telling me that it is decreasing. Okay, it is decreasing at a rate of 7% per year. Okay, so we're gonna call A the initial population. I know that we don't have it, but we should be able to deal with it. So we're gonna call A the initial population. The initial population. It means the population when t equal to 0. I called it A because they don't give it to me. And we're gonna call P of t population at time t. And now what's the formula for P of t? This is a population which is decreasing at a rate of 7%. So P of t, because it's decreasing by the same percent, this is exponential function. This is an exponential function. So what's the formula for P of t? It's A times B to the t, where B, we have to figure it out. But what is B? The growth rate here, since it's decreasing by 7%, the growth rate is minus 7%. Minus 7%, it means minus 0.7. So it means the B is 1 minus 0.07, which is 0.93. It means every year the population is 93% of the year before it. So P of t is A times 0.93 to the power t. So that's the formula for the population. Don't worry about A. Now what's the question? How long for population to be cut in half? It means the population is A. How long it will be to be cut in half? It means how long it would be to become half what it was. That's the time. How long it be to be half of it. So it means we need to find the time when the population is half its initial value. So we have to find the time when the population is half its initial value. So how do we do that? We're going to set the population equal to half A and solve for t. Right? Was anybody able to do that problem? So let us repeat a little bit what we are doing. I have a population. They tell me it decreased by 7% every year. So every year is 7% decrease. It means every year, 93% of the original population remain. 93% remain. Over time, the population, because decreasing, it will become half of what it started with. And the question is, how long it take for the population to be half its starting value? So if you start at 1,000, the question is how long it take to become 500. If started at 2,000, how long it's going to take to be 1,000, and so on and so forth. So the question is how long it take the population to be half its started value. Now, not giving us the initial value will not be problematic. Actually, we can handle it. So now the question is, I need to solve for that. So I need to solve for the time. All right, how will I do that? I feel I'm talking a lot. Now I need to get back to you. How would you solve for t? Don't be afraid of not knowing A. It will not affect the problem. I have to divide, I have to isolate the exponential. How can I isolate the exponential? I have to get rid of A. How to do that? I have to divide by A. And as you realize, when we divide by A, the A is gone. We don't have to worry about it. We divide by A, and I will have this equal a half a over a. My a is gone. And then I will have 0.93 to the power t equal a half. So the reason they did not give you a, because you actually don't need it. The a will eventually be simplified. And now I have to solve. Now how to solve? We have to take the natural log from both sides. So I can bring the exponential down and I proceed. So we do that very slowly. So I have now 0.93 to the power t equal a half. We're gonna take ln from both sides. Okay. Now let's see, what do we get? I will have ln of 0.93 to the power t equal the ln of a half. Now my t here is the power. And it's this t that I can bring it down. So this is going to become t times the ln of equal ln of a half. And now I solve for t. I will get ln of a half divided by the ln of 0.93. And now we're going to see how long it takes for the population to reduce. So I need ln of a half divided by the ln of 0.93. And I will get 9 point, it's gonna take 9.55 years for the population to be reduced to half its value. Okay, so the population was, whatever the population initially is, it doesn't really matter. What's gonna do is after 9 years and a half, the population will be reduced to half its value, regardless what it started with. So the time it needs to be reduced to half its value doesn't actually depend on how fast it's going down. It doesn't depend on what's the initial value is. Okay. All right. This brings up actually a definition of a half-life and a double time. So let me define this clearly. So doubling time. Doubling time. Suppose I have a function which is an exponential function. Okay. What's the doubling time? Suppose I have a function which is increasing, an exponential function. Then the doubling time so that's my population. It starts here and it's increasing. I'm taking this case. At some point, the population is twice what it started with. The doubling time is how long it takes for the population to double its value. So double time is the time period. It's the time period needed for an exponential function to double its initial value. For an exponential function to double its value. Okay, so the doubling time is, suppose you have a function which is increasing. At some point, the initial value will double. 1,000, 2,000, 3,000, 6,000. The doubling time is this, the doubling time. That's how long it takes. So that's the doubling time. How long it takes for the population to double. Okay. And the half time, so this is the half time is the half time. Or sorry, the half-life is called. Half-life. Suppose an exponential function is decreasing. Suppose f is decreasing. The half-life is the same thing. There's a time period for an exponential function to decrease to half its original value. So the half-life is the same thing, but how long it takes to go down to half its value. So if the function is decreasing, then the half-life, so that's my function, is decreasing. This is my A. And at some point, it's half A. And this is the half-life. And that's what we did a minute ago. We found the half-life. So the half-life is the time period needed for an exponential function to decrease to half its value. To decrease to half its value. Okay, so they are not hard definitions. So doubling time, if the function increasing, how long it takes to double its value. Half-life, how long it takes to decrease to half its value. So we're going to do one more problem along those lines. And this time I'm going to ask you about the doubling time. And then we proceed. Okay, so here's my problem. And I want you guys to do it. So here's my problem. Example 1. Okay. The population in a certain town. So the population in a certain town grows according to the following formula. So that's how it's growing. So according to the formula that P of T, the population, is 100 times 1 point, let us say 145. Okay, so that's a population. Its initial value is 100 and it's growing. Its growth rate is 1.45%. That's the growth rate. Question is, find doubling time. Find the doubling time. Okay. All right, I'll give you a minute to interact. It means, what do I need to find? Find the doubling time. I want you to set up the equation we need to find that. And anyone who understands the question, please write it on chat so I can move on. Find the doubling time. Okay, I need to find the time, right, such that what happened? So we're gonna find T such that what? I want an equation such that what? Such that the population is equal, doubled. It means the population will be equal to what? The initial population is, let us say 100, because in this particular problem, I gave you the initial. It means we have to find so that the population grows to 200. That's really what the problem is. So finding the doubling time is actually find the time when the population is 200. So basically, I need to find the time here. What is this? Now, how do we do that? Okay, I have the population. I set the population equal to 200 and solve for T. So this is 1.145 to the power T. Okay. Back to a simple problem where I have an equation where the unknown is the power T and I need to solve for it. So I isolate my exponential term by dividing by 100. And then I will have 1 point that to the power T. If I divide this by 100 is equal to 2. So finding the doubling time or the half-life is not actually, once we understand the meaning, it's not really hard. Now I take the natural log from both sides. Equal the ln of 2. And then, as usual, I bring the t down. It's ln equal ln of 2. And now I solve for t. I divide, remember that this is a number here. That's a number. So I divide by it. So we're going to divide by the ln of 1.145. So it's going to give me the ln of 2 divided by the ln of that. And we pick up our calculator and I evaluate this term. So if I evaluate it, okay, thank you very much, Matt. I get 5.119. Means almost 5.12 years. So which means that in 12 years, that's my doubling time, the population will actually grow from 100 to 200. So that's the idea of doubling time and half-life. So if function is decreasing, we talk about the half-life. If it's increasing, we talk about doubling time. Okay, please, any questions before we proceed? All right. What I'm going to talk about it now is the following idea. We talked about exponential functions. So let us a little bit recall something about the exponential. So far, every exponential, we wrote it in the form initial times growth factor to the power t. That's how we wrote every exponential function. 1.1 for the growth doesn't seem like, yep, yeah, it doubled because, you know, it's compounded. I mean, it's a good question, but the question that it's compounded means every year it's growing more than the year before. That's really what's happening. You know, the first year it grew by 14.5%. And then the second year it's going to grow by 14.5%, but over a more population because the population already got bigger and bigger. But yeah, that's what happens. It's an exponential growth. Exponential growth is very fast. Exponential growth is very fast. Okay. I mean, that's why the virus that we had, that's why the COVID-19, when it's growing exponentially. So that's why it's growing very, very, very fast. That's really what's happening in there. So suppose the function is a times b to the power v. Exactly. It's like compounding interest, a section that I had to skip in this course. Usually I cover compounding interest. You're absolutely correct, man. So suppose f of t is a times b to the t. Very good. And what we saw so far, we wrote it this way, and we talked about its graph. So let's remember how the graph looks like. Okay, its initial value is a, but the graph depended on b. So let us remember, when b is bigger than 1, and b is bigger than 1, the picture is like that. This is t, and this is a times b to the t. So if it started at at 0, it's a. Then we multiply, after 1 unit, we multiply by b. So if b is bigger than 1, let us say b is 2, 1.2, the numbers get bigger. So if b is bigger than 1, my exponential function is increasing. And if b is less than 1, it means it's decreasing. Okay, that's really was the graph. Let's take an example here. Suppose I have t, and let me take b, whatever, let us say b to be 1/2. So let me take b to be 1/2. So this is a times 1/2 to the power t. What's the effect? At 0, it's a. At every unit, I'm multiplying by 1/2, so I'm making it smaller. I multiply by a number less than 1, I'm going to make it smaller and smaller and smaller. So b less than 1 is decreasing, b greater than 1 is increasing. So that's what we know about exponential. Now, what we're going to see today is the following. a way to rewrite exponential form. So we're going to find a way to rewrite exponential form. And why we do that? Because there is one good reason, is that calculus will be easier with the new form we're going to write. So my question now today is another way, and it's important for us, another way to write an exponential function. Another way to write an exponential function that involves e. Okay, let's see what we're talking about. So as I said, so far, exponential have this form. A is the initial, B the growth factor. Okay. Now we can rewrite. And the word rewrite is important. We can rewrite A times B to the power T in the following form. A times E to the KT. Okay, we're gonna rewrite. Of course, I have to explain where it's coming from. And we will explain by an example. Okay, so the idea here is that so far, every exponential function we had, we wrote it in this form. But I'm telling you today that we can rewrite it, not change it, rewrite it in the form A times E 2 to the KT. So what is the K, what's the E, and where is this coming from? And I will explain by an example, and then we'll take the rule. So let us say, suppose we have the following. So example 1. And you have to help me out a little bit. Suppose I have a function. Suppose f of t is written in this form. So let us say 100 or 1,000 times 1 plus 2 to the power t. And I want to rewrite it in this format. So where is this e coming from? What's the k? What's this whole thing coming from? All right, I need the following fact to be input to understand. If I take e before I move further, e to the ln of 1 over 2, this is equal to what? Anybody? I would like to practice this idea a lot today, so you have to help me with answer. It's 1.2, absolutely correct. Now I'm going to take f of t, and you have to be patient with me. There is algebra involved, and I'm going to not change it. Be very careful. I'm just going to manipulate it algebraically so I can write it this way. It's going to be equal to 1,000 times. Now, instead of 1.2, I'm going to play a game and write this to the form e to the ln of 1.2. Notice I am not altering anything. I am rewriting. 1.2 is the same as that. Okay. This is equal to. Now I'm going to use property of exponent, which is the following. One of the property of exponent is that if you have a n to the power m, you multiply the power. Why? I'm going to use this. So I have this e is just a number, to this power, the whole thing to the power t. That's the same as e to the power ln. I'm going to write it here clearly. So that's the same thing as 1,000 times e to the following power, ln of 1.2 times t. Okay, which is what? Let us compute ln of 1 over 2. ln of 1.2 is just a number that I can pick up my calculator and do it. And if I pick up my calculator, I will get 0.1823. It means this function, I can rewrite it as 1,000 times e to the following power. So instead of that, I'm going to replace this by its value, 0.1823 times t. Okay, so let us sum up the way I am rewriting things. So the function 1000 times 1.2 to the power t can be rewritten, and rewritten, we're not, as I repeat, it's not different. We can rewrite it as 1000 times e to the power 0.1823 t. And where is this 0.823? Where is this coming from? This is nothing more than the ln of the b, ln of 1.2. Okay, so every function written the way we know it can be rewritten as a, remain the same, e to the power ln of 1.2 times t. Okay, so this means that f of t, I rewrote it as 1.2 to the power t, so that's equal to e 1000 e to the kt, where the k, this k here, is the ln of b, which is the ln of 1.2. So that's really how we're going to rewrite it. And then, so every function written this way can be rewritten as 1000 e to the kt. And what is the k in here? The k was nothing more than the ln of 1.2. And why we're doing this trouble, and you have the right to complain, if you guys study calculus, this is easier to work with than that function. This is easy and this is harder to work with. And that's really why we learn it, and you have to learn it very well. So let me sum up the first part of what we did. So I'm going to sum it up in a general case. I'm going to have two summaries. So in general, if f of t has the form a times b to the power t, I can rewrite, and the word rewrite is crucial, I can rewrite it as a times e to the kt. That's what I showed you so far. And my k is the natural log of the growth factor. And this k is called continuous growth rate. It will be called continuous growth rate, which I will write it clearly later on. Now, suppose I'm going to go backward. Suppose a function is given to you this way. How can we back up? So now, suppose, because it could be written either way, suppose somebody tells you that f of t is the following form. It's 1000 times e, let us say, to the power minus 0.03t. So somebody gave you the exponential in this form. How do we go backward to here? So suppose this is the case, and my question to you is rewrite it. And as you realize, I'm rewrite in the form 1000 b to the t, the regular format. So let's see how we're going to do that. I will explain by an example. So, okay, this is equal to that. And I'm going to write it as b to the t. So I want this e to go in a way. So how I'm going to do this? Watch carefully how we're going to do that. I'm going to rewrite this as 1000. I'm not going to change. This piece, I'm going to use some algebra on it. And I'm going to rewrite it in the following form. This is t, and e to the minus 0.03. That's all I need to do it. Okay, so I'm using the properties of exponent all the time. It's a n times m. So in my scenario, a is my e, My n is minus 0.03. My m is a t. So this is equal to e to minus 0.3 times t, which is equal to 1,000 times. That's going to be my b, e to the minus 0.3. So if I compute that number, that's going to be the b. That's the b that I'll be looking for. That's the b. So if I just evaluate this using my calculator, I'm getting 0.9704. Okay, where the b is e to the minus 0.03. Now let us summarize this, and then I will repeat summary for both of them. So if the function f of t is given to you in this format, k to the t, then I can rewrite it in the form b to the t. And what's the b? The b is actually, you can in your head, you can either memorize or in your head think about it. This is the b. That's the b for me. The b is e to the k. So any exponential in the future will be given to you in two formats. Either they'll give it to you like this, or they'll give it to you like that. And the relationship between them, if it's of the form e to the kt, then the b is e to the k. If it's the form ab to the t, and then the k is the ln of b. Now I'm going to totally summarize this in one big summary and 2 tons of examples to elaborate this. So let me do the summary. So if you guys are writing, you will have it. Here's the summary. Any exponential function can be written in two forms. A times b to the t, or a e to the kt. So we can write them in either format, they are the same. Now, what's the relationship between them and the name? K, if it's written in this format, this k here is called the continuous growth rate. This k is called the continuous growth rate. And the relationship between the k and the b, that this k is the ln of b. So if I have a function given in this format, I can write it in this format. The k is the ln of b and is called the continuous growth rate. Now, vice versa. If a function is written to you this form, I can rewrite it in that form. And what's the b? The b is e to the k. So b, that we call the growth factor, and it's equal e to the k. Okay, so this is the relationship. So if I know b, I know k, it's the ln of b. If I know k, I know b, it's e to the k. Now, important idea. If a function has the form a times b to the t, and b greater than 1, the function is increasing. B less than 1, the function is decreasing. Now, what about k will help me to know whether we have an increasing or decreasing exponential. Here is the idea. If this k is positive, so k is a positive number, 0.0, 0.1, 0.03, positive number, then the b, so this is the exponential function in general. That's how the exponential works. If I plug in a positive number for k, a positive number, so positive number, then e to the k will be bigger than 1. It means we have a growth. So if the k positive and you take e to a positive number, you get a number bigger than 1. E to the 0 is 1. After that, it's going to be bigger than 1. So if k is positive, we're going to have a growth. If k is negative, e to the k is less than 1. In other words, suppose you take e to the power minus 0.03. My k here is, if k is minus 0.03, my k is negative. This number is basically 1 over that. This will be less than 1. So if k is negative, the b will be less than 1, and we have an exponential decay. So that's the general dichotomy for here. So if my function, and after that I do only problems. So this is for a times b to the t. B bigger than 1, increase, less than 1, decrease. If I write it a e to the kt, so if I rewrite this in this format, then this will be the scenario. Positive k, increase, negative k, decrease. And the relationship between those is that b is e to the k, or k is the ln of b. That's the relationship between all those ideas. Now we're going to practice problems, and I want you guys to have your calculator in front of you, and you're going to do them together because I want to make sure you full understanding of that. So I will put the problem very simple, but I want you to do them yourself. So problem number 1 is the following. Okay. I'm going to take f of t to be, let us say 100, e to the minus 0.01 t. So I wrote this function in the form e to the kt. My question to you is, first, identify k. What is k in this problem? And what we call k is continuous, that's the word, growth rate. So when they tell you continuous growth rate, it means they are talking about k. So question number 1, identify k. Question number 2 is f increasing or decreasing? So simple question, but question number 3 is rewrite f in the form a times b to the t. Okay, you have 2 minutes to do everything, and then I get back with you. What's k? Continuous growth rate. Is f increasing or decreasing? Then I want you to rewrite in the form f of t equal a times b to the t. Are we ready? First, k. So k, I'm having answers. K is this one. Come next to t. That's what we call the continuous growth rate. So the k is minus 0.01. Now, is this function increasing or decreasing? What can we say? K is negative. It means my function immediately decreasing. Means if I graph it, so this is my function so far. It starts at 100, that's the initial, and it's decreasing. So it's going to go like that. The last part, I want you to write in the form a times b to the t. So here we have to remember the relationship between b and the k. So f of t is equal 100 e to the minus 0.01 t. I want to write it in this format. The a remained the same, but what's the b? The b is e to the k. That's the b. That's to B. You can think about it this way. That's to B. So it's equal to e to the minus 0.01. This b will be less than 1 because k is negative. So if I evaluate this, e to the power minus 0.01, I'm getting 0.99. I hope I am right. So this will give me 0.99 to the power t. Okay, so we converted this function to this format. Okay, that's how the conversion will work, that you have really to understand. I mean, I want you definitely to be able to go back and forth between the two forms. Okay, I'm going to do a second one, but please help me out, all of you. Please work it in front of you. Number 2. The question is the same. This time I'm going to give you f of t to be, let us say 1,000 times 0.8, for example, 81 to the power t. So this time my function is of the form a b to the t. And the question is, I want to rewrite it in the form a e to the kt. So I'm going to go backward. So let us remember how it works. So rewrite in the form a e to the kt. All right. So we're going to rewrite it in this form. So f of t is 1,000.81 to the power 3. I want to write it under this form. The a will remain the same, but it's the e. So e to which power? kt. Now what's the k? Let us remember the k. The k is the ln of the b. My b here is 0.81. It means it's the ln of 0.81. It means this is equal to, and one of your classmates is giving me the answer. It's minus 0.211. Okay, so that's my k. So it's going to be minus 0.21, and that is the t in here. So that's how we converted to this format. So it means that if you take any value of t, whether you plug it in this formula or you plug it in here, you get the exact same answer. Those are the same function, but written in a different format. No more, no less. That's the same thing, but written in a different format. Example number 3, again, suppose f of t equal, I'll go back and forth between both formats. F of t equal, let us say 10 e to the 0.2t. And question is, write, question number A, write in the form a b to the t. That's the first question. And then once we do that, I want to ask you several different questions just to make sure you understand the terminology. Please get going and write the answers. Remember the relationship between them. The main relationship you have to know is that b is e to the k, or k is ln of b. So if you know one, you know the other. That's the relationship that you have to get going. Okay. I want the answer. I'm going to pick up your answer. I don't want to feel like doing it myself. Okay, and anybody else? I have some answer which is sent to me privately. I want others. Okay, that's better. Okay, so we have in the form. So here my K is 0.2. So my B is E to the 0.2. And we need more. Actually, I can copy your answer because, all right, we're having trouble. Let us see what E is. B is E to the power 0.2, which is 1.221. So that's 1.221. Do not confuse. B is E to the K. Be very careful. So what is f of t is going to be equal to? A remain the same. That's my A. And B is 1.221 to the power t. That's the way we rewrite it in this format. And I repeat, one way you can check yourself, plug in 10 for t here. Plug in 10 for t here. You should get the exact same answer. Plug in 100 here, 100 here, you get the same answer. Means those two functions are the same, it's just the writing is different. Okay. Now question number B is, this question is for the terminology. Identify the following. Continuous growth rate. As I said, this question is to get the terminology going. Growth factor and growth rate. Okay, let's see what the terminology tells me. Continuous growth rate, it means the K. That's the continuous one, which is the 0.2. The growth factor, it's the B, which is 1.2 to 1. That's the growth factor. The growth rate that you're still having difficulties with. The growth rate is 1 plus the growth rate is the growth factor. That's really the relationship. Intuitively, if B is 1.22.1, it means the population every year, the function is 122.1% of it was the year before. It means it grew by that much. That's the rate of growth. It means it grew by 22.1%. So the growth rate is 1 plus the growth rate is 1.2 to 1. It means the growth rate is 0.2 to 1. Which is 2.21%. No, sorry. 0.1%. So it means that this function represents something that starts initially at 10. It's growing by 22.1% every unit of time. So the growth rate tells you by how much it grows every unit of time, by 22.1%. The growth factor tells me that every year it's 122.1% of what it was the year before. It was what it was plus the rate of 22.1%. Okay, so that's the terminology that we have to use. Okay. Question number 3. I'm going to tell you the following. Suppose you have a population grow according to this following formula. P of t equal, let me give you something, 54 times e to the power 0.013t. So this time it is an exponential, and I gave you the formula, not the regular formula. I gave you using e to the kt. And now the question to you is the following. Question. Find the growth rate, not the continuous one. Means if a population growing according to this, what is the growth rate? It means t is in years. It means by what percent it's growing every year. This does not really tell you quite by how much it's growing. I need the growth rate. Means what do I need? I need by how much it's growing every year. K is called the continuous growth rate. It doesn't tell you by how much it's growing per year. It's a formula that helps us to rewrite an exponential and easy to work with, but it doesn't tell me by how much it is. So if I want to find the growth rate, what do you think I need to do? Back to you. Rewrite, exactly. I'm gonna rewrite to find what? B. So to find the growth rate, first I need to find my B. Once I find my B, I find the growth rate. So what is my B? B is, if this is this, so I'm rewriting to find my B. B, if you ever forget it, that's really the B. The B is a constant, 0.013. So that's the growth factor. And then I figure out the growth rate. Now I compute that number. So e to the power 0.013. And I'm getting 1.0. So we're going to get it to 4 decimal places at least, actually to 5 decimal, because I want to distinguish it from that. 13084. Okay. That's the B. So now I want the growth rate. The growth rate is 1.03084 minus 1. It means 0.03084. Okay, which is 0.3. What am I doing? Sorry. My mind is going blank these days. Okay. All right. So if I have a function in this format and I want my growth rate, I find my B, and then from there we go after the growth rate. Example number 3. Suppose we have again a population and it's growing according to the following formula. Okay, so the population in Washington State, I guess those numbers are right. In millions. Is given by f of t equal 5.4. Remember, this is in million. E to the power 0.013t, where t is the number of years. Is the number of years after 1995. It means that t equal to 0 correspond to the year 1995. So that's the population in Washington State. And this is the same example I took a minute ago. It means the population is growing at the rate of 3.084% per year. That's really the growth rate. But now I'm going to ask you the following question. Find the doubling time. Okay. So that's how long it's going to take the population in Washington state to double. So this is, it starts at 5.4 million, and it's growing according to this formula. You want to use this formula, and the question is how long it takes to double. It means to be twice that much. It should be a lot of time, but let us see. Okay. So what do I need to do? I have to find t such that the population is twice the initial population. The question is how long this is gonna grow. Now I can set p. I know, I use p and f because I like to use p for population, so I'm gonna stick to p. Okay, so it means I need to set 5.4 times e to the 0.013t. I don't have to convert. I can use this formula now. Equal 2 times 5.4. Okay, I don't have to convert because I'm not asking you to convert. In this problem, I'm just asking you to find the doubling time. So conversion is not really necessary. I can work with this formula. I don't have to convert every time. So now I need to solve. So I'm going to divide by 5.4 both sides. And this will give me equal to 2. So as you realize, the initial value always get cancelled out. So we're going to divide by that. So the initial value doesn't really matter. What matters is actually how fast the population is increasing. Now we take the log from both sides. And see how long it's going to take. So it's going to give me ln of e equal the ln of 2. Now, this is here the power. And my power is 0.013. So this is the power that should go down. So now I'm going to have 0.013t, that's the power that went down, times the ln of e, which is 1, equal the ln of 2. So it's going to give me that 0.013t equal the ln of 2. Now I find the t. ln of 2 divided by 0.013 and find the doubling time. And this should not be hard. ln of 2, anybody found it? 0.0. ln of 2 divided by 0.013. Anybody found this faster than me? 53.3, almost 53 years. Yeah, I got 53. So let us really sum up a little bit. This is, I mean, the numbers here are right. That's really the population in Washington state. So this is accurate. And in 1995, the population was 5.4 million. It's growing according to this formula. And based on what we did a minute ago in the previous problem, it means the growth rate was 3.084%. So that's how fast it was growing every year at the rate of 3.084%. And it doubles in 53 years. So this shows you that actually not a lot of time. In 53 years, it's going to be doubling, even though its growth is that much per year. So it's growing very little per year, but it's kind of compounding because It grows 3% out of 5.4 the first year. The second year is much more. So it's growing 3.004 out of this new value. And it's a new value, and it's a new value. So it keeps growing and growing and growing. And then in 53 years, the population is gonna actually double. Right, so the last problem no, I don't have that. Okay, the last problem I would like to do is the following problem, which is actually kind of nice. And here we are. Sorry, I forgot what my paper is. Okay. Give me 1 minute. I'm sorry. I thought I had it in front of me, but I don't. Right. So we'll do a much easier problem, and the other one I'll give it to you next time. All right. So let's meet the following problem. Carbon-14 is a radioactive substance that decays at a constant rate of 0.0121%. And the question is, find the half-life of carbon-14. Okay, so I write the problem down much clearer. So here's the problem. Carbon-14, which is used to basically find the age of people. When people, die, they use it to find how long ago they died. So carbon-14 is a radioactive substance. Okay, and it decays along the following formula. Actually, I'm going to change the problem. Along the formula, f of t equal a, I don't care what a is, to the power, it has to be negative, 0.0121t. Okay. Now the question is, find the half-life of the carbon-14. Okay. So we have a radioactive substance, we call it carbon-14, and it's decaying. It decays according to this formula. And as you realize, I put f of t to be a because actually I really don't need the a. And the question is, find the half-life of carbon-14. So first here, let us notice that in this problem, my k is minus 0.012 negative. It means we definitely have decreasing function. So here we have a chemical product, a carbon-14. It starts sometimes at a value A. And my question is, okay, how long it takes for it to become half of what started with? That's really my half-life. Okay. So let's put this down. So what's my question here? So question is, we need to find the T such that f of t is half of a. That's for half-life, half of its original value. It means a times e to the minus 0.012t equal the half of a. So we're trying to work with that. So let us divide by a. So give me e to the minus equal a half. Now we take ln from both sides. And so on. And now I will get the ln of this equal. equal a half. Now, this is my power. And this whole power, I need to bring it down. So I will have minus 0.012t times the ln of e. ln of e is 1 equal ln of a half. And finally, I will solve for t. And so I will have minus 0.12t equal ln of a half, and this will give me my t, which is ln of 1/2 divided, and there is a minus in here, 0.012. And then the rest is simple. We just plug in number, and it's gonna give me ln of a half divided by 0.012. It's gonna give me okay, whatever. So it's gonna give me 57.76 years. And that will give me the half-life of this chemical product. Okay. All right. So at this note, I actually will finish the course. And next time, I'm going to assign homework as usual. I definitely urge you to do the practice problem, and you will go through them. And then I will talk about the review for the exam. You guys know that the review is already on Blackboard. As usual, I urge you to do the review. And we talk about the final, and if you guys have any questions about it. And as usual, we're going to have the quiz, which will be based on everything I did today. So the main idea with it today, we did a lot of problem solving, but the main idea is this conversion between a b to the t and a e to the kt. And as I said, exponential will be given to you in either format. In either format. That's really the main idea that today. The b, if you know the k, you know the b. If you know the b, you know the k. So that's the idea. And then b bigger than 1, we know that that's increasing. B less than 1 decrease. When you have the k, it's whether k positive or negative. That's what decides whether it's increasing or decreasing. Okay. All right. Any questions? You guys are so quiet today. It was hard to teach you. Any questions? Okay, please, when you come on Thursday, I want the homework to be done. And I'm going to assign again the problem that I've assigned for today because you have a quiz. So I'm sure you're going to do them and we discuss them. Okay.
Professor,
any question before I let you go?
Yeah. How does that conversion make it easier for calculus?
The derivative. If you've
Okay.
ever seen calculus before, differentiating this function is much easier.
Okay.
That's that. That's as simple as that.
Okay.
So in calculus, most of the time when they introduce exponential function, this format is used most of the time. I mean, most of the time we use this format. More than that, to be honest. But this one helped me understand more what's going on. In what sense? What sense? Because if I tell you the population is 10 times 1.2 to the power t, all right? Where the unit is million. I know exactly what's happening. In what sense?
You know, it's growing by 20% every year.
Exactly, exactly. Immediately, I understand. It means 20% per year. If it's 10.93 to the power t, I know what's happening. The population is decreasing by 7%. Are you with me?
Yeah.
So this is, I understand. No question asked. Fully, I do and you do. The minute I start to writing e to the kt, it's not as easy to understand. It's less intuitive than that. I mean, I know you can go back to here, but you have to go back to here to be able to understand the annual growth rates.
Okay.
Okay, the K is called continuous growth rate. And there is one section that I skipped, and because, I mean, I had to repeat what happened when I was absent. I had to skip, but all of you will see that if you are business major, most probably, you will see the idea of continuous growth rate. And you will understand the K. The K is intuitively, if you give a person, like if you put money in the bank intuitively, and the growth rate tells you if you invest the money and you get a return almost every minute on your money, what's the rate that's given? So it's not very hard, but any of you who will study business will definitely have to go through what's called the continuous growth rate. It means when you compound something, not every year. Like in every problem I gave you, I told you 20% per year. But sometimes you don't have to do it per year. You can give 20% compounded like 4 times a year. It means every 4 times a year. It means every 3 months, you get 20 over 4% on your money, which is 5% on your money. When this happens, then your actual rate will not be 20%. It's going to be more than 20%.
Right.
Following what I'm saying?
Yes.
Yeah. And now for the continuous growth rate, the idea is that, okay, instead of doing it 4 times per year, why not do it every hour of the year? It means you get percent almost every hour. Now, when you do that, your actual rate will be more than 20%, will be much more. And continuous, it means you do it almost every minute, every second.
Okay.
So it's not very hard actually, but it's unfortunate I have to skip this section. But I had to get to here. I had to get to the whole picture. Okay. So this, you understand it. This harder to understand. This is easy in calculus, more than that. That's really what's happening mathematically. Right? Any other questions?
Thank you.
Sure. Anybody else? If there is anybody else. Anybody have any questions? I'm here. So if you guys have any problem, you can ask. Anything any problems you have, any questions? Okay, so I'll see you on Thursday. Please do your homework. Bye-bye, guys.